What's up everybody, and welcome to part 2 of this tutorial series on using the KITTI Odometry dataset with OpenCV and Python. In the last video I went through all the basics of camera matrices and the math that they do, because that's going to be the foundation of all the tools that we're using here. And so I hope you watched it, I hope you found it informative, and now that we know all that, we can dig into the fun stuff, which we're going to be doing now. So very soon we're going to be able to do some cool stuff like this, where we get to look at, this is a colorized version of the disparity, which is the depth estimated by the stereo, using the stereo pair of images of the left and right camera. And then this is the LiDAR point cloud depth, where you can kind of see the darker dots are further away, but it's all black and white, so it's kind of hard to tell. Either way, and then yeah, that's the actual black and white left camera image. So as I mentioned last time, the let's just Google real quick KITTI dataset and go to their website, because you'll see if we go to the odometry dataset, they have datasets for all these different tasks here, which is really cool. But we'll be playing with this one, and you can see excuse me, that the this is the grayscale cameras, and it's only 22 gigs, whereas these are the color cameras, and it's a lot bigger. And the thing is, you don't really need this, because, or at least not for this tutorial series, because these are actually a separate set of cameras anyway. So if you were thinking to yourself like, oh, well, I'll download the color pictures and then convert them to grayscale, because why also download the grayscale pictures if I already have the color ones? Well, that's not quite going to work, because they're different cameras, and so they're positioned differently on the car. And so you would have to be, it's not that you couldn't do that, but you would need to be adding transformations to the points in those images that we're not going to be doing. So to properly follow along here, you're going to need the grayscale one, and we don't need this. So, you know, don't feel obligated to download a giant 65 gig pack of images that we're not going to be using. So, you know, what could these be useful for is, okay, for visual odometry, which is what we're going to be doing, all you need is grayscale. And as a matter of fact, the feature detectors in OpenCV that find parts of the pictures that it matches to other pictures to figure out where the same object is in that picture, which then we use to figure out 3D motion, those all work in black and white, because they're looking for gradients. They're looking for changes in brightness, you know, from very dark to very light, so that they can find edges, and especially they want to find corners. And then they have fancy ways of making that rotation and scale invariant, so that it can, you know, if things rotate a bit or get smaller or bigger, then you'll still be able to find the same images, or I mean features in the image. So that's all done in grayscale. So why would you want color pictures? Well, later I'll talk about this more, but with the color pictures you could actually do things like object detection and in figuring out what's in the image, because when you if you have a car in front of you or a bicyclist, you know, going beside you on the road, then those things are not static. They're moving alongside the car. And so if you're using those parts of the image to try and figure out how far the car has moved, then, and you're combining that with static objects like trees and fire hydrants and whatever, then you're going to be getting mixed information. It might throw your estimate off, and it probably does, but we'll see that so, you know, the color images could be used for, you know, these other tasks that make the task that you're doing better. But that's more advanced stuff, so, you know, maybe I'll put out a tutorial on that one day. But for now, we're just going to be doing the regular black and white feature matching, structure from motion kind of thing. And also because we're going to be using a version of the PNP algorithm that uses Ransac, and so basically it'll throw away outliers that don't match the transformation that it comes up with. And so that'll probably do a good job all by itself of ignoring dynamic objects, as they call them, or objects that move in the image that aren't static, stationary. And so anyways, before we can do any of that, we need to get our data set into a nice convenient place where we can access it easily and not have to keep worrying about loading things or where they're located on the computer. So what we want to do is make ourselves a dataset handler class that we can just attach everything to and then work with that class object to access our images and our LiDAR and ground truth and everything like that. Just put it all in one place. So this is going to be it. I'm going to actually code it line by line. But there's something I want to mention before we get into it, which is that when I first wrote this handler, I was taking all of the images in the sequence on the hard drive and then loading them into lists which were attached to the handler. And when you do that, it loads all of those images into your RAM at once, which I didn't even think about because one sec. If we look at my task manager and go over to performance, we see that I'm using 31.3 gigs of RAM right now, and because I have 64 in this laptop, but a lot of people aren't going to have that much, and most notebooks, even nice ones, are going to have like 16 unless you modify them. So in order for people to follow along with this, I'm not going to be able to use the same way I wrote the handler the first time, so we're going to use generators, which is probably the way I should have done it in the first place. But generators are useful when you're working with sequences of things, because we're not actually going to be using all of the images at one time, so there's no real reason to have all of them loaded into memory at once. We're going to be using, one at a time basically, but actually we're going to need to have a buffer of one because we're going to be comparing one image to the next image. So we'll be keeping a buffer, but that's exactly the point, is that you don't have more images loaded into your memory than you need at any one time. And we will compare the difference, because I'm going to write the handler class so that it can do either one. And you can see here I loaded up like 2 example instances where I said dataset handler, and then I'm putting in the sequence number, and then it loaded all of them up into memory. And then here we have handler 2, which is a dataset handler, but I've put the argument low memory equals true, meaning you don't have 64 gigs of RAM in your computer, and you're not going to, you're going to use the generators. So we can look at the only real difference here is going to be if I run this code block, which is going to really quickly run a little image sequence in the background. So each image took like, 100th of a second to load. Whereas if I run the same code with the handler that has all the images attached in lists, you can see it basically didn't take any time at all to load each image because every image is already loaded. So that would be the only reason it might be beneficial to have them loaded into your memory, is if you're really working with trying to shave off every possible millisecond. But for our purposes, this 100th of a second is not going to make any difference, and so we're going to run with the generator version of the class, and I'll get into that more. But just to make my point clear, you can import garbage collector is GC here, and then so I'll delete the handler object, and then you can see my memory just plummets in use down to 11.2 gigs. So that class object was literally holding up 20 gigs of RAM on my computer. So if you only have 16 gigs of RAM, you wouldn't even be able to load that class object. So that's exactly why we're going to make the adjustment. So anyways, enough blabbing, onto the coding. Generators are a really useful thing to know how to use. I feel like, when I was learning Python and stuff, it didn't really come up much because, we weren't dealing with giant data sets like this. But in this case, we're going to use them. So starting off, we're going to need to import our packages. We know we're going to need CV2. I'm going to use OS. I'm going to need matplotlib, lib.pyplot. I'm going to use pandas. So I'm going to try not to use any special packages. I don't consider pandas to be special. But we're also going to use NumPy and anything else. Okay, I'm going to use datetime because I want to time things. So that should be enough to go with for now. And so let me just I'm gonna me 1 second, bear with me, I'm winging it. So anyways, the first thing we want to ask ourselves is how many frames are in our sequence, because different sequences may have a different number of frames, we don't know, so we want a convenient way to check that. And so if you set up your file path the way I have and the way I advised for the tutorial, you don't have to, you can just modify this line of code here in order to point to wherever your KITTI Odometry dataset is located. But for me, I have the dataset in a folder called dataset, which is in the same folder as this repository. So if I want to access it, I put a double dot because it's going to go up a folder from the repository into the folder where the dataset and the repo are both together. And then I have it in a folder called dataset. And then so in your dataset, you have poses and sequences. The poses are your ground truth poses provided by the research team. And then sequences is all of the sequences of images and LiDAR clouds that go with that this particular sequence. So we go into sequences and we can see that we have 22 different sequences. So that's cool. We'll go with the first one. And then what's in there, we have calib.text, which is our calibration information, image 0, which is our left grayscale camera, and image 1, which is our right grayscale camera. So probably should have brought this up by now, but anyways, when you download your version of the dataset, you don't need the color images. We're not going to use these. We're only going to use the grayscale because feature matching algorithms. Oh yeah, I did talk about this. Anyways, yeah, so we only need these grayscale images, and they're going to pop up over here as image 0 and image 1. I suppose if you had the RGB images, they'd have image 2 and image 3 here. And like I said, that would be useful if we were doing more advanced stuff like object detection and whatever, but we're not. So, you know, let's just talk about the left camera image for a second, because we can see if we hit tab again, we got all these PNG files. So this is going to be the sequence of frames in the left camera, and that'll be at this file path. So one thing you can use that makes this really easy is if we say left images equals, and then I say os.listdir file path, whoops, path, and then that gives us a list. You can see type of left images is a list, and that list is going to be the actual string names of each of the files in that directory. So we get a list of strings that tell us what each file is named. And so in order to figure out how many frames we have in the sequence, all we have to do is just say the length of left images. And we see that we have 4,541 frames in this sequence. And so that's useful information, and we're going to need that. So let's go ahead and just look at one of these images, and we'll use matplotlib, I guess, to do that. And we'll say plt.mshow and cv2.mread, and we'll say file path plus left images, first left image name, and then I'm going to pass in this flag of 0, which tells CV2 that I want to read it as a grayscale. Probably don't have to do that because it already is grayscale, but just to be, you know. And so here we have our first image, and it's in this weird purple and yellow color scheme that Matplotlib uses, but it's kind of cool. And so let's make it a little bigger, actually, so we can see more of what's in there. Say fig size equals something like that, I guess. All right, so get a little bigger, and we see there's like a mopedist in front of us, car. We got buildings everywhere. It looks like we're in kind of like an apartment-y residential area. And yeah, so keep track of what's in the content of that image. And so now that we've seen what an image from our camera looks like, we see it's like nice and wide. We can find out, probably should copy this out real quick and assign it to a variable so that we can play with it for a second. Just say first image equals exactly that. And then let's say first image.shape and see how big it is. So it's 376 by 1241 pixels, which is a pretty aggressively wide aspect ratio for an image. And so that's cool. That'll give us plenty of stereo width to find disparity in and get our depth estimations with. And so let's look at a point cloud now. And so this is going to take a little more finesse. But let me say, we'll just straight up load one. So these point clouds are loaded as binary files. And so we're going to reference our README real quick. Bear with me a second while I get there because I didn't have this. So we go to databases, KITTI Odometry, dataset, sequences, and oh wait, no, I went too far. In your dev kit, that's where the README is. So we're looking at, scroll down to where it's talking about the LiDAR, and okay, this is where it is. Velodyne point clouds. So this data contains 4 times number of values, where the first 3 values correspond to X, Y, and Z, and the last value is reflectance information. So that's pretty cool that they include that. As far as using the LiDAR for depth, you don't need that, but it's cool to have, and we can definitely take a look at it. But the thing to know is that it's going to have 4 columns or 4 rows, depending on which way you orient the matrix. But and so they talk about here how it's saved as binary files to save space, and so they give you some code here that I think that's C++ to load it. But luckily, as Python programmers, we don't have to worry about converting the binary file to numbers. We can just use NumPy. So we're going to splice in here, and I'm going to redo this little part of the video where I was covering up what I was doing. And so the first thing was that I did not import pandas and NumPy as these aliases because I was talking. So pandas is PD, NumPy is NP. And get them where we need them. Whoa, hold up. A little aggressive there. Okay, so as I was just saying in the video, was that when we're using Python, we don't have to worry so much about the fact that we're reading these binary files because NumPy will do that for us. We have to be a little careful how we do it though. So we're going to load a point cloud. We're going to say point cloud equals np.from file. And then, so make this easy on ourselves. We'll look back at our file path. It's still set to this, so let's just, here, tell you what. We'll copy that. We're going to bring it down here. File path is that, except not with the image. We'll just set it to the sequence folder because I'm going to say file path plus Velodyne. Yeah, and that's got to be a string slash, and then we're going to have the name of the file, which we can get real quick by saying Velodyne files equals os.listdir file path plus Velodyne, right? So that'll give us the names of all the files that are in that folder, and then we can just say Velodyne files 0. So this is going to be into the dataset, into the sequence folder, into the Velodyne folder, and then the first file, which is what we're after. And so it's going to be informative for me to do this the wrong way and then fix it. So we're going to say that's our point cloud, and then we're going to set up, we're going to want to be in matplotlib notebook for this. So we're going to use our magic command matplotlib notebook, which will let us see things in 3D and drag them around and stuff. And then we're going to go ahead and set up a plot figure, plt.figure, fig size equals, we'll say 8 by 8. and then x equals big dot add subplot in the very first position, and this is where you write projection equals 3D. And then so when we look at the Velodyne file, we saw that there was 4 pieces of information for everything. But so let's actually look at what our point cloud looks like right now, because we know that it's a NumPy array. We just made it, so the type of the point cloud. And then so point cloud dot shape is just a really long list of numbers. So we need to reshape this to get the information that we're looking for, and our README file told us that we had, for every measurement, we had X, Y, Z reflectance. And so there's 4 things. So we should be able to say point cloud equals point cloud dot reshape, and then say -1, 4. And this is going to set it up to where it's got 4 columns that represent X, Y, Z reflectance. You could easily do 4, -1, and then that would give you 4 rows and a bunch of columns. In my brain, I like to think of it as 4 columns, so I'm just setting it up this way. But at any point, you can just transpose using NumPy to change the orientation of your matrix, so it really doesn't matter. Captain's choice. And so now we can look at point cloud.shape, and we see that we've got 4 columns and this number of rows. So our x's are going to be point cloud all rows first column. Y's are going to be point cloud all rows first column, and z's are going to be point cloud all rows second column. And then we say ax dot scatter. I'm gonna, yeah, we'll say plot first and see why you can't do that. But anyways, say x's, y's, z's, and then I'm gonna, yeah, I think this will be good enough for us to see right off the bat here. Okay, so this is exactly why you can't say plot, because it's gonna join all these points together. So that's a big no. So we're going to say scatter. Okay, and so here we have some nice beefy dots, and things are looking kind of strange. So what we do is we use S for the size of the dots. We're going to set it really small because there's a lot of dots. And okay, so something has gone wrong here, and because this is not the way the point cloud is supposed to look. And so what it is that if we go to full screen here, and I promise I won't cover it with my face this time, and go to our README file, then we can see that they've mentioned that these are 32-bit floating point numbers. And so NumPy is trying to read this in as, did it tell us that when I said this? D-type. Yeah, it's loaded it in as float 64, and so that's wrong. And so when we're up here, we need to explicitly tell it that the D-type we want, D-type equals np.float 32. I'm also going to say count equals -1. Actually, I'm not. Let's just do it like this. And so you see how now we've said that they're 32-bit floating point numbers, and we run this again, and we can see that we have twice as many values now. And that's because we were not decoding the file, the binary file, the way we were supposed to be, by letting NumPy make up its own mind and say that they were 64-bit. So that's why it looked bad. So when we do this again, and here we have a proper point cloud. So a couple of things that are annoying right now is that when I drag it around, it is laggy. And that's because there's like a billion points happening right now. So one thing you can do if you're really getting bogged down is you can index and say you want every 20th point, just like this. And this is what that means, is that it's only going to take every 20th one. And so that works, and you can see it slides around a little less laggy now. And that's all well and good, but you're not getting all the information, and we're really not going to be doing this for very long, so I'm going to actually comment that out. It's just a useful little tidbit to know. And I told you I wasn't going to cover this up, so here we are back on the screen where we're supposed to be. And so another thing that's annoying about this is that the vertical axis is on a totally different scale from this axis. So we're looking at 2 meters as being, you know, the same size as 20 meters over here. And that's just not going to give us the visual understanding that we're looking for here. AX dot set box aspect. And I don't know exactly why this works. I just Googled around and found this solution, but it's probably not worth going into in this video anyways. But just so you know, if you want to get your axes on the same scale so that they're, you know, a meter is a meter in every direction and it makes more sense, this is what you do. np.ptp in each one. And then also, I'm going to go ahead and say ax.grid is false because that's not going to, it's just going to get in our way. Axis is off because that's also going to be just cluttered. And let's go ahead and set our x label to x, ax.set y label to y, ax.set z label to z. And yeah, I think that should work. Okay, so now we have an actual point cloud here. Oh, you know, one last thing I want to do is to avoid trying to figure out which way the car is pointing. I already figured out which way to start it off. So view init is going to be elevation equals 40 and azimuth equals 180. And this will point us in the direction that the car is actually looking in. Okay, so this is our point cloud. This is what we're looking for. In Matplotlib Notebook, if you right click and then drag toward yourself, you will zoom in. And it's going to take a second because there's a million points. But we want to see HD. So, all right. Probably a little too much. All right, no, this looks pretty good. I don't want to overdo it again, but you can see like this car over here, you can see it really well, and then the LiDAR beams are blocked by it, so there's just like empty space behind it. And over here as well, here's that mopedist slash motorcyclist that was riding in front of us. And so, you know, this is, it's pretty detailed. And so really the point cloud would be very useful if we were going to be trying to create a localization map, which is sort of probably what the next tutorial next series will be after this one, because in this one, I mean, it's complicated enough just to do structure from motion from the cameras. And but really structure from motion drifts over time. And so there's, especially with this data set, like usually you would be doing mixing visual data with like GPS and IMU information that would help you, you know, whatever errors you get in one can be, you know, corrected by the other periodically, where once things don't agree, you can kind of snap yourself back where you're going. But with this, we're just working with visual odometry. So as it drifts over time, we don't have very good ways to correct the accumulated error that's going to happen as we keep making, you know, our best guess at how the car moved in each of these 4,500 frames. You know, all of those little errors that we accumulate along the way are going to add up, and we really don't have a way to like correct that. So one thing that people do is they take all the LiDAR clouds of each frame and they create this 3D map where everything sort of stays there, where it tracks the positions of objects in 3D so that you can localize the car against that map as well. And so we're not going to be doing that, but I thought it would be cool to look at the LiDAR cloud because it's pretty. So anyways, there's a little bit of data set exploration. And so now we know we can list our files, we can navigate to the folders, we can do all this. So it's time to make our class. And so we make a class, we're going to call it Dataset Handler. And so we're going to pass some arguments into this. Whoops, not there. Make our init function. I'm all over the place here. So, okay, so we're going to want to know what sequence we want the dataset handler to load. We're going to want it to know whether we want it to load the LiDAR information with it, which I'm going to set to true as default. But, you know, let's say you want to follow along, but you don't want to download the 80 gigabyte LiDAR file, then you could possibly do it by passing LiDAR equals false, but it's really better to have it. I'm going to put this progress bar equals true because I'm going to use progress bar on the thing is purely for aesthetics, but you don't have to use it. And as a matter of fact, if we're doing the low memory, which I'm putting in now, you don't need the progress bar at all because it's not going to load the images into RAM. It's just going to set up generators that will load the images later. So that's the whole point of a generator, is that it doesn't load something until you need it. I think I went over that already. So we'll set up some parts of our class here. So we're going to say self.lidar equals lidar, so it knows whether it has that in its class or not. Self.low memory equals low memory. When you set these Boolean flags like this that are attached to the class, then that way later if you pass the class into a function, then that function can determine what that class, how that class is set up, so then it knows how to use the object that you're passing into it. And so we're going to set up our sequence directory is dataset. It's always good to like tab your way through this so that you avoid any spelling errors or just forgetting where things are. And just put a thing on there. You can use an F string for this, but I honestly find that harder to read than using the dot format on the end of a string. So we're going to do it this way, but do it anyway. Like poses directory is dataset sequences. Follow my own advice. Whoa, hold on. So that's going to be where the ground truth file would be located. And again, format with the sequence number that we're after. And then, so let's go ahead and set up, this will be, I did load pandas, right? Yeah, but I didn't put the alias. I don't know what I was doing up here. As PD, I was talking. So let's just say that, okay. I like using pandas to read CSVs. I just think it's easy. And then, so we're going to say self.poses directory. Okay, so you can figure this out yourself, but I'll just let you know the delimiter in these files is spaces, and then there's no header. All right, and then, so now we're going to do what I did before, which is get the list of the names of all of the image files so that we have something to iterate through when we go to grab them. And I'm going to attach them to the class. So say self.left image files equals os.lister of self. Sequence directory plus image 0, because that's going to be the, yeah, write image files, os.list self.sequence directory plus, should probably copy and paste here, but sometimes I feel like typing is even faster. Just bear with me here, we got a little bit of stuff to go through before we can dig into all the juicy things, but I feel like, you know, this video series is oriented at people who are like learning how to do this stuff. So, you know, obviously if you already were like a boss at doing visual odometry and stuff, you wouldn't be doing it in Python, first of all, but this is supposed to be like a educational experience. So make sure we don't do any typos here. Python's really cool. It's slow. That's the problem, is that in real world applications, you need this process to be super speedy so that it can, you know, fire off a whole lot of frames per second and do this in real time. Python is way slower, but the coolest thing about Python is that you can program in it dynamically, so that whenever, as I'm explaining things and demonstrating like the point cloud up there and stuff, every time I run code, I don't have to recompile it, you know, and do all the C++ stuff. You know, with Python, it's a lot more easy to just play with your data and do things sort of on the fly. And so, you know, if you really get into this stuff, you're going to end up needing to learn C++ because that's the industry standard. I mean, you know, you can't keep up with Python, but understanding how this stuff works and playing with the data and exploring it and, you know, learning this whole thing, Python's going to be just fine. So we want to know how many frames are in the sequence. So we just say self.left image files. We're going to take the length of that. And so now the class has a variable attached to it that's called number of frames, so that if we ever need to establish the number of frames in this class, we can just call that and not have to repeat ourselves all the time. Self.sequence directory and then plus Velodyne, just like we did before. So all I've been doing here for the past couple of minutes is just setting up. Now we have a list of our image file names in the left image files directory, the same thing for the right, the same thing for the Velodyne. We have the number of frames established, and we also have the path to our LiDAR files that we'll need to use later. So, because when it comes to these image files, it's directly in the sequences here, whereas the Velodyne files, you need to have the word Velodyne there. And so, anyways. So now we need to, I didn't talk about the calibration file in this video. I really covered that in depth in the last video, but just because I want to be self-contained in case you skipped the last video because you already knew about camera matrices, let's look at the calibration file. So I'm going to say calib equals pd.read csv, and we're going to say dataset, oops, another reason the tab is just the way to go, so that way you know you're actually really doing this properly. Sequences 00, and then calib.text, yes sir. And so same thing, delimiter is a space, the header is none. And then so let's look at what we get when we put that out. Okay, so we have 5 rows, and I guess I could have mentioned that index column is 0, so index call equals 0. Load again. Okay, so we have P0 through P3. These are the rectified projection matrices for each camera. So we'll only need the first 2 because we have the black and white cameras. These are the color cameras. TR is the transformation matrix between LiDAR coordinate frame and the left camera's coordinate frame, so that if you want to take the 3D points that are measured in the LiDAR scans and put them into the frame of the left camera, this is the matrix that you would use. And so anyways, there's 12 columns here, and that's because they've flattened out 3x4 transformation matrices. So if we say calib equals calib.reshape I think we can do it like this with pandas. We'll find out. No, I can't because okay, no, pandas doesn't do reshape. So let's just look at let's look at the LiDAR transformation matrix. So we'll say tr is calib.ilocate the 5th row, which is known as 4 in Python, and we'll say reshape into, well, I guess pandas does have reshape, but you can't do it on a whole data frame like that. So we'll do this and look at print tr. Okay, it doesn't. I lied again. So we're going to turn this into an array by forcing it into an array by writing that. There we go. We've got a 3x4 transformation matrix between the LiDAR coordinate frame and the camera coordinate frame. I talked all about what a transformation matrix is in the last video, so if you don't know, you shouldn't skip that video. Go back and watch it. So that's what we're looking at anyways. And so here we have poses. We've loaded it in as the data frame, and so when we want each piece of information out of that, we're just going to say self.p0 equals np.array of the poses. Oh no, what? Sorry, folks. Yeah, we need to, that's the poses, which we should probably just go ahead and extract our ground truth information. I'm just going to call ground truth GT, and this is going to be your matrix of poses, and we're going to set up a zeros array that is in the shape of the, well, actually, so I'm going to take this because I want to use this num frames variable that we set up, which is why we have it, is exactly for things like this, where we set self.numFrames is our first shape dimension, and then we have 3x4. So this is going to be a matrix, or a tensor really, that is has an index length of the number of frames that we have, and then for each frame we're going to have a 3x4 matrix that will be the ground truth pose. And then so we can say for pose in, really, let's just say for I in range of the length of poses, we'll say self.gt that I index value equals an array of the poses dot I locate that same index dot reshape 3x4. And so now we get, we loaded up our zeros array and filled it in with the information from our poses. And notice that there is no self.poses here because we don't need it after that. We're through with it. Same with the calibration file. When we do this, read CSV self.poses. Well, actually, is it? No. Okay. This is sequence directory plus the words calib.text. Okay, and then the delimiter again is space header equals none. I realize this is going to be a long video, but you know, it's not a simple task that we're doing here. So anybody who was in for the ride of following a video tutorial series on doing structure from motion with the KITTI dataset, you know, hang in there. We're doing it. This is it. So P0 is going to be an array. We're going to say calib dot I, or rather, let's do, yeah, okay. This is like a kind of a weird way to do it, I guess, but when you use a pandas loc command here, you're going to do it by the name of the index, which in this case is we saw. Oh, did I get rid of that cell? Silly. I don't even know what I did. I thought we were looking at the calibration file just a second ago. Could have sworn. Doesn't matter. For real though? I guess so. Oh, you know what I did? Is I got rid of it. Yeah, here it is. So yeah, here's the indices, and they're like strings. So I'm indexing it that way. You could use an iloc, which I was using earlier, where you use a number. Anyways, moving on. So we're gonna do the same thing that we did before. We got to do it for everyone. I'm gonna go ahead and just load them all in there, because why not just be thorough so you don't get tripped up later if you were to try and do something. Let's just do this quickly. It's been a long day for me, folks. Okay, and then we're gonna just go ahead and get the transformation matrix for the LiDAR as well. And these are all just conveniently attached to this dataset handling class now. We never have to worry about doing any of this again. That's why we're making this class, because we want this data available, callable. Don't want to have to load from the directory. We don't want to have to reshape anything. We just want it there. So that's why we're doing this. So this is where things get interesting with the memory thing that I was talking about. We're gonna do it both ways. We're gonna have the option of doing if low memory, which I should probably just set to true, because most people are not gonna have 64 gigs of RAM. So if low memory, and then so here's where I'm gonna get a little tricky with it. Let me think about how I want to do this. Okay, so with a generator, it's going to be an iterator, and then you're going to use this. Let me just, I don't know how much y'all know, but why? Let's just say test gen equals. When you make a generator, you can use this like list comprehension like notation, but you use the parentheses instead of the brackets. It's an awesome thing to know how to do. So we'll just say that the generator gives you I in range 5. And then so if what you do to get one of these values out of the test generator is you say next test gen, and you get 0. And then if I run the same cell again, it's going to give me a 1. Now it's going to give me a 2, and so on. Now the thing is that as it loads its way through, it forgets about the last iterations, because it's moved on. And so if you want to reset the generator, you just reinstantiate it with the same thing, and now we're back to 0. So I'm going to throw another function inside of our class here that specifically handles exactly that, where if we want to get back to the start of the sequence of images, then we run this command, and then that'll set up our images back to the start of the sequence. So we'll say self.images left equals cv2.mread, and we'll say self.sequence directory plus image 0 / plus name left. So that's going to be the variable, which we're going to say for name left in self.left image files. Because remember, left image files is a list containing strings that are the names of the files that we're trying to load. So we're iterating through that list of names of files and reading cv2.mreading this thing. And I'm going to put a little 0 here to tell it to read it as a grayscale. That's redundant because it's already a grayscale picture, but it's good to be thorough sometimes. So, and this is the thing, is that if you had done this with brackets, then you would be saving a list of these images to your class, but that's going to load up your RAM with every single image file all at once, which could be useful to some people, but it's going to take up 20 gigs of RAM, and you better have it if you're going to do that. So instead, what we're doing is we're making this generator. So I'm just going to copy and paste this. And same exact thing, except we change that to 1, and we change this to right. And, so we'll keep everything making sense here. Okay, and we're going to do the same thing for the point clouds. Plus Velodyne file D type. Just like earlier, remember this is very important. You got to tell it float 32 or else it's going to decode the information wrong. Reshape -1 4 is how we did it before. Now, and it's like you could do this as 4 -1, and then you would have 4 rows by, you know, however many thousand columns, or you could do -1 4, which would be 4 columns by however many rows that you've got. And I'm doing it as columns because in my brain that just makes more sense to do it vertically. But this is going to mean that we're going to have to transpose it later when we want to apply matrix algebra, because when you do a dot product with the transformation matrix, if that transformation matrix is, you know, 4 columns, then it's going to need 4 rows to multiply into, so you're going to transpose it. But it's very easily done with NumPy with a little .t at the end, so we're just going to do it like this. And so this is where we say for Velodyne file in self.velodyne files. Right on. So that's reset frames is going to set these variables attached to our class as these generators. And that's exactly what we want. So earlier when we said if low memory, we want to right off the bat just say self.reset frames, and then that one command is going to take care of setting all 3 of these variables up. And conveniently later, as we're working with the handler, if we run handler.reset frames, it'll set us back to the beginning of the sequence. And so that'll be super handy. And so in this low memory scenario, I think that it's generally pretty helpful to have like at least one image file just there so that you can look at it or run some tests with it without having to run the generator. So I'm just going to make another variable first image left, and then do a cv2.mread of all of this stuff again. And instead of name left, we're just going to do left image, well, it's got to be self. Oh, break the line. Plus self dot left image files 0, because that'll be the first left image there. I'll say self dot for, you get into this whole copy and pasting thing. I like typing too much. Right, image files, image 1. All right, so that'll set us up with some preliminary images that we can use, and it may even be helpful to have a second image left. So let's just run it, second image left, because we're going to be testing one of our functions on a sequence of 2 images. So let's just do that, just so we don't have to worry about it later. That's 1, and that's done. Okay, and then same for a point cloud. First point cloud. And again, the reason I'm doing this is because as you run the generators, you're gonna, be sequencing through. And I don't know if this is efficient or not. You probably really don't have to do this because I set up the reset frames function so that it would always reset you back to the start. But I feel like it just gets too easy to, like, if you're writing a function that's playing with point clouds and you're generating a point cloud every time you want to test that function, then you would have to remember to reset your frames every time you had tested that function, or else the next time you run your scheme, your indexes on your generators may not be lined up, and you need them all to be exactly the same if this is going to work out. So I feel like having these solidly attached just makes it easier not to screw yourself up. But if we were being strictly efficient and like trying to save every little bit of memory that we could, this would not be the way. But with, like I said, if you're doing this in Python, we're not like worried about efficiency as much. The only reason we're even using generators is because there's so many files that people literally can't even fit it on their RAM. Oh, here's a good reason to go ahead and load an image in, because we want the self.mHeight and self.mWidth variables so that we can use that information later on. So we got that loaded up. So that's the low memory scenario, probably the one that we're going to continue with for the rest of this tutorial, since I'm assuming most people don't have more than 20 gigs of RAM. But I like to be thorough, so we're going to say if it's not low memory, I'm going to use progress bar here. So, and I put this progress bar equals true up here if you want. This is purely for aesthetics, but I like it. So we're going to get that. If you don't have progress bar, you don't want to deal with downloading progress bar, don't worry about it. I'm going to set it up in an if statement. Just when you make your handler class, just pass progress bar equals false. This is just for aesthetics, but this is how you do it. Anyways, if you do want to use progress bar, say max value equals self.num frames, and that's it. So that'll start the bar if you want it. And then for I name left in enumerate, I don't even think needed to do that. Oh, okay, I see why. And remember, this is the list of image file names that we have. So we get name right equals self.image right image files, same index. And then we can go ahead and say, okay, one thing to do here is to go ahead and set up empty lists. Images left equals empty list, self.images right equals an empty list. And you could have done this with list comprehension. I guess I'm really going out of my way to use this progress bar here, so whatever. It works out the same way, so it doesn't matter. Images left append, and we'll do cv2.mread self.sequencer. I could copy this and paste it, but I honestly think that this is just faster sometimes. That way I don't have to go through and like change all the little pieces. Name left. Right, because we're iterating and we're unpacking name left there. And then self.images right.append cv2.mread self. Probably should have warned y'all. This is, it's a lot to be done, but I figured if you were interested in this kind of thing, then you would be on board. So if you're still here, what's up? Okay, so this is where, I guess I should have said this before as well. Yeah, so I'm going to stay consistent with if LiDAR, because I told you that we were going to make this so that people didn't have to have LiDAR if they didn't want it. I mean, I'm going to be using LiDAR through this tutorial, so you should probably have it, but just to demonstrate, I guess, we want to make this so that you can run this without LiDAR if you want. So anything that deals with LiDAR is going to be in these if statements. We already have LiDAR path. Oh. That's a little confusing, but we'll just do it anyways. LiDAR path plus self.velodyne files I. And then we'll load a point cloud in the way that we were doing it up here. So we will copy and paste that. Oh no. Dumb. Right, see, I'm already messing up over here because this needs to be D-type equals float30 mp.float32, or else it would have been messed up. So lots of little things to keep track of here. Don't let yourself get messed up. I guess I was passing count equals -1 too. I'm just going to stay super duper consistent because I don't want to get messed up. The count equals -1 should be completely unnecessary because that tells it that you want all of it. So you shouldn't have to say that, but it's one of those things. I didn't even put in the reshape, man. Slipping. So maybe this is what I should be copying. I'm putting this over here. I don't have to do this because I already set up LiDAR path as a thing, but you know what, I'll just delete that entirely and say self.velodyne files, right, that's the thing, yep. I, and now we have it. Okay, and put it on the list. And if progress, sorry, bar.update. This is all you have to do for progress bar, so it's nice and easy to use. I'm like a progress bar salesman over here. I'm like, use it, it's pretty. It lets you know how long it's going to take. That's pretty cool. You don't just see a little running cell. You have no idea if any progress is being made. Alright, so we're setting up these m height and m width in a different way than what we did before, because now we actually just have these things loaded up. Okay. Alright, we're getting there. I think that that's pretty much it. So I'm going to put a pass down here. Alright, I think we're ready to run this thing and see if it works. So we'll say handler equals, and I'm going to go full screen just so we can watch this thing fill my RAM up because I find it somewhat entertaining. So let's pull up this task manager again. What the hell is going on? Oh, it is working. Okay, sorry, it did not tell me that it had switched windows. So we'll say handler is dataset handler, and the sequence number that we're passing is 00. I did not include a doc string, so we'll just see what these, okay, we do want LiDAR, we do want progress bar, and I'm going to set low memory equals false because we're going to watch what happens if you do. Low memory. like that. I mean, it's right there. Low memory, did I misspell it? Low memory, no. This is tripping me up. I'm probably looking like a super noob right now, but it's kind of confusing me why it is telling me that that's an unexpected thing. This is one of those things that it's like probably making me feel pretty stupid here. Low underscore memory, low underscore memory. I don't know. I'm just gonna say fuck it. And I mean, do you pass it up here? I didn't think that that was the way that it worked. Let me just try this real quick. It is. I really thought that, anyways. I'm fucking up over here. Let's okay, well that clearly did not work. This is killing me. Like usually I just don't know, y'all. I'm just gonna set that to false and do it that way because this is it's being weird. I mean, y'all are looking right here with me, so I'm not crazy. This is the way a class object. Oh, you know what I did? I said diff class dataset handler class. Okay, that is exactly what was wrong there. I was like, I didn't think that I was this fucking bad at Python. Okay, so now we're gonna do it the way I said before. Memory equals false, and now we get more errors. Set sequences 00.text. Right up at that. You know what? This is supposed to say poses. And more errors. Cannot interpret 3 as a data type. I bet you can't, because we need to wrap this up into a tuple. Probably did that a couple more times, to be honest with you. So attribute blank clouds. Yes, because I did not establish an empty list. Self.blank clouds equals empty list. Yeah, we did it. It was only like, what, 4 errors? It's not that bad. Anyway, so as you can see, it's going to take a little while, and so maybe I'll just blab about something for a while. So I don't know how long it's been. I think it's probably been a pretty long time, and so what we're going to end up doing in the next video is we're going to do these 2 functions probably, which is not that one. Compute the left disparity map, where we take the left and the right images from a stereo pair, and then we use CV2 to match them and create a disparity map. And a disparity map, as we were looking at in that video I showed you right at the beginning of this tutorial, looks like this. And so you can see it's really kind of nicely looks like your depth, where lighter colors represent more disparity and darker colors represent less disparity. And what that means is that between the 2 cameras that we're looking at the scene, once the stereo matcher decides what the same points are in those two pictures, then it looks at the two pictures and figures out how far apart they are in the two pictures. And so just like with how your eyes work, things that are closer to you appear further apart. Like if you shut one eye and then shut the other eye and you have your finger right in front of your face, your finger is going to move a lot. Whereas if your finger was a mile away and you shut one eye and shut the other eye and looked at it, it's going to stay in the same place. So that's exactly what we're doing, is we are creating a disparity map from those two images. And so we see the dataset handler over here is loaded up. And I said that we were going to watch the memory fill up and then totally covered it up. But yeah, see, we're back up to 32.1 gigs of RAM being used in order to hold this handler object here. And so that's just not feasible for most people. So we're going to say handler2 equals dataset handler, same sequence, but run it with the default parameters. And we have a problem. Name LiDAR is not defined. I think I was supposed to say if self.lidar. Or how I did that up here. It didn't bitch at me here. What's up with that? Oh, because, okay, this is actually being called in a different function, so it doesn't know what LiDAR is outside of init, so we had to pass it there, so that's it. You see how quickly that loaded? We didn't have to wait, what, a minute and 47 seconds? It's for the birds. We don't need that. And then, so we can see now, if we do cv2.mshow, well, let's do plt.mshow. We already put it in 3D matplotlib, so I'm going to go back to full screen here and say, whoa, it's me again. Looks like I was about to cover the code with my face. So here we are where you can see it, and we have our handler classes set up. And so we're gonna just pop back into matplotlib inline so we can see the stuff in the notebook. And then we're gonna say plt.mshow, and we're going to say handler.left image, oh, it's actually images left 0, and go ahead and look at it, and we have an image. So that's how you would do it if we had these lists of images attached to our gigantic handler class. But if we're going to use the class that has generators, which I'm assuming most people would be, then what we would do instead is plt.mshow, and we'd say handler.images left, except instead of indexing it with 0, we're going to use the generator call and say next. Whoops. Oh, because it's supposed to be handler2. And there you have it. So, I wonder why that one's black and white. That's interesting. Oh, you know why? Because when it came to these, I didn't put the 0 in here. So that's interesting. That does make a difference. Well, yeah, so if we reload this handler... Well, anyways, you get the idea. With the generator version of the class, you do this, and with the gigantic list containing class, you do this. And so back to the regular video, and there you have it. So yeah, same thing, different ways. I showed you in the beginning that, you know, the time to access the picture is going to take a little longer with this one, but for our purposes, this is just fine. So anyways, I think I'm going to cut the video off there. You have everything you need to know to create this wonderful dataset handler class that we've created in order to do everything that we're going to do from here, which is going to be super exciting and fun. And I'm glad you're sticking with me here. So thanks for watching, and catch you on the next video.